So today we are going to be doing lesson 5 in our unit on circuits, which we're going to be talking about Ohm's law. And Ohm's law addresses resistance. So let's start with what we already know. We know that things that are hard require energy. I have discovered this a great deal on my exercise bike. It is hard, it requires energy, and that's the whole point of an exercise bike. So let's relate that to what we're going to be dealing with here. And that is, in circuits, things that make it harder for the current to flow use the energy in the circuit to do work. What does that mean? Well, let's show some examples. Light bulbs. Light bulbs are an example that we have all the time, right there. And so light bulbs have a resistance. They make it harder for electricity to flow through a circuit, and they then do work, which is a bright idea. Okay, that was a bad pun. All right, so we also have electric motors, and this is a diagram of a starter motor of a car, which is an electric motor. It uses that electric power, uses that electric energy from the battery in order to spin the engine and then get your car started. Heaters, like these heating elements on top of a stove, are a resistor. They provide resistance to the flow of electricity. They do work. In this case, they heat up dinner. This also limits the flow of electrons through a circuit. Could also be called, they resist the flow of electrons. So they resist that flow of electrons. They resist the current. What does this look like? And that then goes into Ohm's law. So Ohm's law is talking about how the greater the resistance, the harder it is to push electrons through a circuit. And then voltage is what gives those electrons a push. That's what sort of pushes the electrons down the wire. And resistance slows their motion. And the rate of motion is called the current. And so in equation form, this looks like V equals IR, where V stands for voltage, I is the current, and R stands for the resistance. So the unit for resistance is an ohm, named after the physicist that came up with all of this. And the symbol for it, or the symbol of the unit, is going to be an omega. So it's a capital Greek omega. So it basically looks like a funky horseshoe. So this is kind of difficult to wrap your head around. In the whole voltage, current, resistance, you've got three things that you can't really visualize. But I found this great cartoon that shows what's going on really well. So the voltage is trying to push electrons down the wire. And those electrons going down the wire is the current, which is of course measured in amps. And ohms, that's the resistance, the measure of resistance, is restricting that flow, making it harder for the electrons to travel. And as part of that resistance, work gets done. So let's look at how we can use this new relationship, Ohm's law, to determine what we really care about when dealing with electric circuits, and that's using it to do work. And work over time is, of course, power. So we know that the higher the voltage, the greater the power. And voltage is that energy per unit charge. And the greater the flow of charge, that's the current, the greater the power output. And we get this in power equals IV. Power is the current times the voltage. Now, resistors are what use electric power. Everything that uses electric power has a resistance, but they slow down the electric current. And this is Ohm's law just rearranged a little bit. So that current is going to go up, the higher the voltage, the higher the push, and going to go down, the greater the resistance. So we have this equation. But what we could do is also put these two together. We could glue these two together, and what we could come up with is one example of gluing these together, and that's going to be power equals I squared R. And there's a bunch of other different substitutions that you can do and solve, etc., etc. But the reason why I included this particular one is because I am a geek. By this time, you have probably realized this. But as a young geek, I learned all of my nursery rhymes from my father. And I learned all the usual ones, like Twinkle, Twinkle, Little Star, power equals I squared R. So, I learned that long before I understood any of this Ohm's law of what power really was, what resistance was, what I was doing, and why was that the symbol for current, and what was a current anyways. So, this is a wonderful equation that I'm throwing in here, only because there's a wonderful mnemonic to remember it. So let's do an example of this. So here we have the bulb from an automotive headlight, and it has a resistance of 2.6 ohms. And then of course it's hooked up to the car battery, which is running at 12 volts. So what is the current through this circuit? And then we also want to find the power output for the bulb. So let's use Ohm's law. So that's going to be the V equals IR. And specifically, we want to solve that for I. We want to solve that for the current, because that's what the question is asking for. So the current is going to equal the voltage divided by the resistance. And we can go ahead and plug some numbers in here. So that voltage, that's going to be 12 volts. And that resistance, that's going to be 2.6 ohms. And remember that funky horseshoe symbol is the Greek letter omega, which is going to be our unit for resistance, or ohms. All right, so now let's see. We can plug that into the calculator and we can come up with 4.61 amps. And as far as currents go, this is pretty high, but it's what's going through this light bulb. We know this because the math works out. All right, so let's see here. Now we figured out what our current's going to be. Now we want to find the power output for this bulb. So power equals IV. So we could also use the power equals I squared R, but in this case I think IV is going to be easier. It's because that allows us to avoid that square and one more math mistake that we could make. So throwing some numbers in here, 4.61 amps, that's what we found in the previous part of this problem. 12 volts, that's the voltage of the battery, that's what's given to us. And we can then solve, and we find that this is a 55 watt light bulb, which is really good because that's what it says on the box. All right, so hopefully you can now start using Ohm's law in order to solve some of the problems, and I wish you the very best of days.